Okay, so here we have this question. A closed cylinder with radius 3 centimeters. So I'm just going to draw that one and say that's 3 centimeters. It's full of water apart from a toy submarine floating at the top. So that's the submarine. And the submarine comprises of a flexible membrane filled with air, has a mass of 14 grams and initial volume of 28 centimeters cubed. So mass equals 14 grams and volume, I'll just say I volume initial equals 28 centimeters cubed. When I press down on the plug at the top, so I exert a force downwards, um, on the plug by a certain amount, the submarine will sink. But how much can I press the plug down before the twist starts to sink? Now the water is incompressible. You may take the density of the water to be 1,000 kilograms per meter cubed. So I think before anything, I would convert the density of water to rho W, which is 1,000 kilograms per meters cubed. I'm going to convert that into uh, grams per centimeters cubed. So this will be 1,000 times another 1,000 grams per meters cubed, and then it will be 1, 2, so pretty much 10 times 10 to the minus 6, or 1 times 10 to the minus 6, sorry, and meters cubed. So 1 meters cubed is 1 times 10 to the 6 centimeters cubed. So I'm going to divide that by 1 times 10 to the 6, and this is not minus, sorry. So that's pretty much just 1 gram per centimeters cubed. Alright, so what's actually happening? If we imagine this cylinder, we're just going to redraw. There's water up till, say, suppose there. If I exert some force on this water, because water is incompressible, nothing's going to happen, right? But then because we have this submarine in the middle, any force applied would be straight away go to the submarine. So for it to sink, we know that the density of the submarine would have to be greater than the density of the water because of Archimedes' principles. So we can say that density of the submarine equals mass over the volume. The mass remains fixed and it doesn't change. The volume changes relative to the force. So we can rearrange that to get the volume. So V equals M over PS, or I should say rho S. Now, we want the value of this density to be greater than the value of density of water, which we found as 1 gram per centimeters cubed. So I can sub 1 into there to find the value of V at which over 1. So at this value of, so let me just say density of water, which is 1. So at this value of V, the density of the submarine would be exactly same as the density of the water. So it would just start to sink. Right. Now for the volume, the change in volume, if I draw another cylinder and if there's water all the way there, if there's something, suppose something compressible on the top or any kind of thing, so every time I exert a force downwards, the height of the water would change by a small amount h, and the volume of this part of the water that has been compressed would be pi r squared h. In this case, we have the value of r and we need to find the value of h. So I can sub the value of v in to get pi r squared h equals m over rho w. I can rearrange for h. No, sorry, this won't be the case. So now I forgot one thing. This delta H will be the change in volume from the initial. So this pi r squared H would be the reduced in volume of the submarine. So the actual value of V would be 28 minus pi r squared H, which is equal to m over rho W. Right, now we can solve this. So 28 minus m, because m over 1 equals pi r squared H. I'm going to bring r squared down, so it will be 28 minus m divided by pi r squared equals h. I know that m equals 14 grams and r equals 3 centimeters. I don't have to worry about the units because I changed the density, so units are consistent everywhere. So this gives me 14 over 9 pi, which is equal to h. And if I do this on my calculator, let's see, 14 divided by 9 pi, it gives us a height of 0.495 something centimeters, or approximately 0.5 centimeters to just 0.50 to 2SF.